What happens when a language model's memory becomes so large that it actually slows down the generation of text? As models scale to handle thousands of documents, the key-value cache becomes a massive bottleneck, forcing engineers to choose between speed and accuracy. This paper introduces KVzap, a method designed to resolve that tension by making cache pruning fast, adaptive, and faithful. To understand the solution, we first need to look at the problem, which the authors describe as a trilemma. Current pruning methods either add too much compute overhead, fail to work during the decoding phase, or sacrifice crucial accuracy for speed. The goal was to break this cycle and create a method that works efficiently across both pre-filling and decoding, without losing information. Building on this challenge, the researchers looked at a high-accuracy method called KVzap, which is precise but requires processing inputs twice. Their innovation, KVzap, replaces those expensive calculations with a fast approximation. By inserting a tiny neural network, a surrogate model, into the layers, they can predict the importance of a token instantly, with negligible computational cost. The mechanism relies on a streamlined, three-step process embedded directly in the transformer blocks. First, a lightweight standard multi-layer perceptron predicts an important score for the current token. Second, an adaptive threshold decides whether to keep it. And finally, a sliding window ensures the most recent 128 tokens are always preserved to maintain immediate context. Now, let's examine how this approximate method compares to other state-of-the-art techniques in practice. The authors benchmarked KVzap against 15 other pruning strategies. As shown in this leaderboard comparison on the ruler dataset, you can see that even at high compression rates, their method maintains accuracy that closely rivals the full cache baseline, outperforming concurrent methods which tend to degrade as memory is reduced. Beyond just standard retrieval tasks, the results highlight a crucial win for reasoning capabilities. On the AEIM25 math benchmark, the model preserved its reasoning performance even when discarding over 50% of the memory. Furthermore, because the method is adaptive, it automatically keeps more tokens for complex prompts and fewer for simple ones, optimizing resources dynamically. In summary, this paper demonstrates that we don't need expensive calculations to identify which memories matter. Models can learn to predict their own attention needs instantly. This allows for practically feasible 2 to 4 times memory compression without hardware changes. To explore the full benchmarks, visit emergentmind.com.